Assalamualaikum warahmatullahi wabarakatuh. My name is Irdina Badrusha binti Muhammad Nur Afendi from class Therapeutic 4A, and in this video I will be presenting my poster about research on a wireless electrooculogram or EOG wearable using conductive fiber electrodes. So firstly, let's start with the introduction. Eye movement research provides important insights, particularly for tracking alertness and medical diagnostics. So, electrooculography or EOG works by measuring voltage changes between the retina and cornea as the eyes move. Traditional EOG systems often use gel-based electrodes, which can be uncomfortable for a long-term use. So the study here proposes a wearable real-time EOG system that uses novel semi-dry conductive fiber electrodes, which improve comfort and signal quality. Now, let's move on to how the system operates or the principal operation. The wearable EOG headset features electrodes placed at the side of the eyes to detect electrical signals produced during eye movement. So these semi-dry electrodes, different from conventional gel electrodes, capture the analog signal, wirelessly transmit them to a processing unit up to 10 meters away. So this system ensures a real-time monitoring without compromising accuracy. It could be particularly beneficial in assistive applications like driving, as well as in diagnostic for drowsiness and attention tracking. Here, we can see the block diagram of the wearable EOG system. So the core of the system consists of an ARM Cortex M4 processor handling edge computing, supported by power management SPI and I2C communication. Recorded analog signals from the EOG electrodes are processed and sent via 2.4G BLE radio to remote device, such as a smartphone, where data analysis can be carried out. We also see the hardware setup of the wearable, which integrates a microphone, accelerometer, and SpO2 sensors, making it more versatile. Now, let's take a look at the results and findings. So the graphs here show different EOG patterns detected for blinking, resting, and horizontal eye movements. So the signals were stable and clearly distinguishable, proving the accuracy of the wearable system. So for the first graph, which is for blinking, it shows a sharp spike corresponding to an eye blink with a peak value near 5.25 millivolts. Blinks are typically characterized by a rapid change in voltage, as shown in the graph here. For graph 2, which is for resting, the graph displays the EOG signals when the eyes are at rest, with much smaller and less significant fluctuations around 5.11 millivolts. So this indicates that there are minimal movement while resting. For the last graph, which is for horizontal eye movement, the graph demonstrates a gradual voltage shift as the eyes move horizontally. The voltage drops slightly below 5.05 millivolts, then rises as the movement ends, indicating that the changing electrical potential is caused by lateral eye motion. So, to conclude, this study has successfully developed a wireless EOG wearable system that offers a practical and comfortable way to monitor eye movements. The semi-dry electrodes improve usability while maintaining signal accuracy. This technology holds a promise for applications such as assistive driving, drowsiness detection, and even cognitive research. Future advancement could further expand its potential, making it a useful tool in real-world diagnostics and monitoring. Finally, I'd like to mention the references used in this study. While there wasn't a specific YouTube video directly addressing this project, I did refer to a general EOG videos available on YouTube. So this video helped me understand how eye movements can be captured via electrodes and interpreted as electrical signals. So these videos were essential in understanding the fundamentals of EOG and guided the design of the wearable system presented here, which I will attach the video at the end. And in terms of the article, the one reference is from a journal focused on bioelectric signal monitoring technologies, which I retrieved from MDPI. So that's all from me today. Thank you so much for your attention, and Assalamualaikum warahmatullahi wabarakatuh.
Okay, this is a very short segment on electrooculography, kind of the basis of how it works. So the basis for this is that the eye is actually a dipole. Within the eye itself are different polarities of charge, where the cornea is positively charged and the retina is negatively charged. So the human eye is this electrical dipole, and the voltage differences are occurring between them. So in front of the cornea is that positive, and behind the retina is the negative. So the electrical potential between the front and the back is the basis from which we can use electrooculography. And that potential is called the corneal retinal potential. And it is between 0.4 of a millivolt and 1 millivolt. And that is something that is now measurable. And they're caused by the hyperpolarizations and depolarizations of the retinal nerve cells here. But knowing this, we can hook up electrodes, not even touching the eyes at all, but around the eyes. And these electrodes are going to pick up on relative charge changes based on where the cornea is pointing. So if the right eye is looking to the right, then it'll pick up this positive charge since the cornea is positively charged. If it's looking to the left, then this negative charge of the retina is going to be exposing itself. So as the right eye is looking right, on your electrooculogram, you're going to see it go up. And then if the right eye is looking left, you're going to see a relatively negative charge. And so it's going to go down. And if the right eye is looking straight, it's going to be here. So it's going to become more intuitive to you as you're running your electrooculography lab. You will be moving your eye around, and then at some point you're going to want to switch your gaze and take a quick peek at the computer screen. But this will give you a very intuitive sense of how you're measuring eye movements without touching the eye whatsoever.